Welcome to this video lecture. Today we're going to be talking about process control hierarchy and communication. Specifically, we're going to be talking about a little bit about how a plant, like a chemical plant that we've been dealing with in this class, would communicate with a process control system. Often this is called a distributed control system, or a DCS. The control system may also be communicating with other applications for advanced control or optimization. All right, so I'm going to show a diagram that is fairly common, at least different variations of this are fairly common. So in any automated chemical process, you have the process itself, and as we've been learning, that process is going to have things like actuators. Actually, I'm going to put actuators over here. So an actuator, a good example of an actuator would be a valve or a switch. This is the thing that's actually opening or closing or making some physical change in the process. The process is also going to have sensors. So for instance, if you want to control concentration or temperature, you need to have a sensor to be able to measure what that concentration is and so that you can control it, or measure that temperature so that you can better control it. Okay, so that's sort of the basic level of the process, and in this diagram we're including the actuators and the sensors as part of the process. So these actuators and sensors will communicate back and forth between a control system. So we have simulated control systems using PID controllers. So this layer here would often be called, again, your DCS, or your distributed control system. So that distributed control system is going to be the thing that is reading in. These are typically electrical signals. So your sensor would send a certain current that would represent your temperature or your concentration. That would be read into your PID, into your DCS, which is going to be running all these algorithms, reading in these electrical signals, converting those into temperature or concentration or whatever it might be, running the PID algorithm to output your valve position, or in the case of a cascaded control system, that this would be going from your primary controller, pushing set points down to your secondary controller. So far throughout the course we've simulated a chemical plant and we've simulated this DCS. Remember, we've set up a bunch of different control loops with PID controllers, so that is representative of your distributed control system. So you may do something more advanced. So one thing about a distributed control system, particularly when you're working with what are called single input, single output controllers, is that each controller is kind of just doing its own thing. It's not aware. It just reads in the one sensor and it just spits out the signal for just one actuator. So it's a one-to-one mapping. So if you're trying to control temperature by changing the process heat, that's sort of all that controller knows. It doesn't know anything about changing feed flows, for example, which can impact temperature, but it won't be able to incorporate those. So there's a more advanced level of control, often called a supervisory control, that can take into account interactions between a lot of different sensors and a lot of different outputs in the process. One common type of supervisory control is called MPC, or model predictive control, and that implies that you use a model of your process to be able to make predictions and look into the future, so you can plan out the trajectory of multiple different variables, and you can sort of solve for optimal operation of all those variables, including the interactions between them. So the communication protocol between a DCS system and a supervisory control system, so this might run on some kind of a server, and there's some kind of a communication protocol, and often that is called OPC. Recently this has been referred to as open platform communication. The legacy term is called OLE for process control, which has kind of a weird name because OLE is itself another acronym. So OPC is basically just a communication protocol that allows your DCS to communicate with other servers for doing more advanced applications. Again, this idea of model predictive control, you're doing much more advanced calculations than the simple PID control algorithm, and you're accounting for the interrelations of a lot of different variables in your system and not just a single input, single output controller like the PID controller. Okay, so another layer above your supervisory control is what's called real-time optimization. So this real-time optimization, again, this regulatory control is something that's happening in seconds. If it detects a sudden change in temperature, for example, you're instantly making moves to try and correct that temperature. Supervisor control, you're looking minutes out and you're making control moves on the time scale of minutes. Real-time optimization, or RTO, so here is where you're not quite as concerned with just control of the plant, but rather optimizing it. So you may have changing feedstock prices or changing product prices. You may have changing environmental conditions. The process itself may change over time with things like fouling in a heat exchanger. So real-time optimization can read in a lot of this information coming from ultimately from your process. It's ultimately getting all this sensor information that's going up the chain. You're storing that in a database. You can build models here, and you're solving for what's my optimal operation under this particular set of circumstances. And because those circumstances may be continuously changing as the environment changes or the process changes or even the market changes for your feed and products, this can solve, okay, what's the best way to run my plant so that I'm maximizing profit? So again, there's a communication protocol that takes place between these two. It may be OPC, you may have a different kind of application programming interface. So that's an API, and that's really what we're going to drill into in this module. So this application programming interface. And just for the sake of completing this discussion, above real-time optimization would be planning and scheduling. So here you're mapping out future conditions, again, weeks or days or weeks in advance. So you're trying to figure out, okay, how do I get these particular feedstocks from this place in the world to my plant, and what are the composition of those feedstocks? How is that going to impact my profitability? How is that going to impact how I'm running my plant in these various ways? So what we're going to be covering mostly in this module, we're going to be kind of imitating this. So we're going to be using our plant is our process model. So we have used Collimator to build a dynamic process model, and we're going to be calling that the plant from here on out. So our DCS, or our distributed control system, this would be the collection of PID controllers that we have created. So those are both a part of our Collimator model, really, but think of those as you have your plant, which is the actual physical process, including the sensors and actuators. Your DCS is going to be racks of computers, essentially, that are running all these different algorithms that are doing all the processing and sending out the signals. So what we are going to do, we're going to skip that supervisory control layer, and we're going to work to be building a real-time optimization system. This is going to come up in module 6, but first we're going to establish the communication protocol in order to do this. I actually apologize. It's going to be module 7 where we do real-time optimization. So we are going to work on establishing an application programming interface, which is going to be reading in data ultimately from our plant and our simulated DCS system. So we're going to be figuring out how do we establish communication here between what's going on in our simulated model and then another computing platform. We're going to be using Python, and more specifically Jupyter Notebook, and the API, or the application programming interface, between Jupyter Notebook and our Collimator model. So we want to learn how to pull in data from our model into some kind of application, and I'm going to replace this real-time optimization right now with just a computing resource. And in our case, we're going to be using Python. So we're going to learn how to read up data into our system, and then do some calculations here, and then be able to push that data back down as set points. So we will read in plant data, do some computation here, and then push that data back down as set points into our DCS. That DCS is going to be, these are our PID controllers again. These are going to be calculating what the values should be for like our valve positions and sending those back down into the actuators. So stay tuned. We're going to be digging into this API interface, this application programming interface between Collimator and some Python code that we will develop throughout this module.